Okay, let's start. Today's class we'll continue with rigid body motion. So this is the part where we're going to consider rotation about a fixed axis. So the axis is fixed and the body rotates about the axis. Okay, like another example would be a simple pendulum. Okay, rotation about a fixed axis, which is essentially fixed to a ground frame. So the outcomes are analyzing motion when the body moves about a fixed axis, and then ability to use the parallel axis theorem to find the inertia and use that inertia to describe the motion of the body about a fixed axis. Okay, so here is a caricature of the body, and it rotates about a fixed axis. So let that axis be O, and the center of mass is, let's say, somewhere here, and the body is acted upon by forces F2, F1, F2, F3, and so on. It can also be acted upon by external moments. Okay, I'll just show one. Okay, and when that's true, it turns out that it's best to describe the motion of the body using the normal and tangential coordinates, okay, as opposed to Cartesian coordinates, because the motion can be described about a fixed axis, and as you know, that's tangential normal coordinates are the best for that. So the way we do this is again the same recipe. First, draw the free body diagram. Okay. So the free body diagram will not have the contact point, but that contact point will be replaced by forces. So this point here would have forces. So let's say that the force is OT and ON, and the reason I wrote it as OT and ON is because I'm going to use normal and tangential coordinates to describe the motion. So let this distance between point O and G be RG, and the coordinate frame, as I mentioned earlier, is going to be UN and UT. Okay, any questions on that? So far so good. So the equations of motion are, well, there are three equations of motion like I described earlier. There's F equals ma. So the net force in the tangential direction is mass times acceleration of g about in the direction t. So that is m alpha r g. The net force in the normal direction is mass times acceleration in the normal direction. So that is going to be m angular speed square times rg. And finally, this is describing the rotational motion. You can take moments about the point G, which is the center of mass, and the net moment is Ig. This is the inertia about G times the angular acceleration. Okay, is that clear? So what happens is when you write these forces and write these moments, you will see that ON and OT will appear in the equations, right? For example, in this equation mg, moment about g, uh, when you take moments about g, OT times RG is going to appear in that equation, right? Because that force at O is acting at a distance r from G. Okay, but what will happen in that case is all these three equations would have OT, ON appearing in it. So when you solve the system of equations, typically alpha, OT, and ON, you will have three equations, three unknowns, and it will be harder to solve than if you had it decoupled. So if you had a scenario where only these two equations were a function of OT and ON, and the third one was a function of just alpha, then you would solve for alpha using the third equation, and you could use that information to solve for the other two ones. So in that case, that is to simplify computations. Another method is to not take the third equation, take the moments about G, but to take the moments about O. And the effect of doing that is that effectively, with this third equation, there will not be any external force due to the hinge joint. There will not be OT and ON in this equation. So this is not the right equation. I'll write the equation down. So if you take moments about OT and ON, then this is what you get. So this is how you can efficiently solve the problem. So the first two equations remain the same. They don't change. But the third equation now is about the point O, where O was the hinge point. Okay. So what you need to do is take inertia about O, not about G, times alpha. Okay. So why we did this is this equation will not have OT and ON in it. So it can be used to solve for alpha. For alpha without solving for OT and ON. So once you solve for alpha in the third equation, you can use that value in the first equation to solve for OT and ON. So that's the advantage of changing the way you find the moments. Take the moments about O and not about G. Okay. So then the question is, how do you find IO? Okay. IO can be found using the parallel axis theorem, right? What's IO? IO is the inertia about this point. Okay, inertia about this point is inertia about G plus mass times the distance between G and O. So in this case, IO is IG plus mass times the distance squared. Okay, so really there are two sets of equations. You can either use this set, okay, or you can use this set, and knowing that IO can be computed using the parallel axis theorem. So in essence, once you have those, the way in which you solve a problem involving rotation about fixed axis is to use the same recipe, draw free body diagrams, write the equations of motion, solve for alpha, and then use that information to solve for things like angular velocity, and also angular position if that is asked. So the same three things. Okay, I will not write that down. Maybe I should just write it down. So recipe for analysis. One is FBD, two is EOM, and three is kinematics. Okay.